So my topic today is for the the liquid compressibility effect on the nozzle flow simulations, and also the 3D needle movement, which is I'm checking for the dynamic needle movement. This with 3 degrees of freedom. So we are in the group we are developed. There are two main researchers who are working for the 1D solver, and the rest we are working for the 3D solver for the fire. So as an introduction, I just want to focus more onto the fuel injection event, and the prime focus in my presentation is mainly for the fuel injection. So the present work is the modeling of a typical diesel injection system. So for that, I have considered the injector and its cross section with its major components, and my prime focus now is near to the sac and this needle tip region. So the complete outline of my presentation today is included here. I have a current state of the art. Then I will explain this current setup which I employed for the 1D and 3D simulation, and then a typical injection test case by taking two injection test cases are studied here. Then a brief conclusion with a future work. So in the current state of the art, we have seen before in our previous presentations, there are a lot of research is happening throughout the world, mainly for the field of cavitation. So here I have given some results from the literature. We also have some implemented in the fire solver, the cavitation models. And the second is regarding the fuel injection events. These are some results from the literature regarding the atomization and sprays, which is also implemented in fire solver. Then the third most important is regarding the cavitation erosion. We also saw before in the previous presentations. This is also more critical when we consider a fuel injector. So there are some results shown here with some literatures on the left hand side. And the other more important is the needle motion. So these are all some of the results also from the literature, which I have also included some recent numerical and experimental stuff, especially this work from Argonne National Laboratory. So these are the main components, and that come into our mind when we study about a fuel injection system. So what I observed from this literature study is like when an injector is considered, its movement, like the lateral and radial movement, is really important. So I took this for my present study. Then the eroded nozzle holes. This can provide a real asymmetry of the flow, which is also really important. And then the liquid compressibility effects, which we will see in my results. So these are the three main key parameters which I considered for for in this case, and which I think is more important. So the current setup is comprises of a 1D 3D coupling interface. So this is the 1D side where it completely resembles a cross section as I shown also before, which has a common rail here with different components with the needle, and there is a fire link between an interface 1D and 3D interface. This 1D solver is a boost height sim solver, and there is an interface here which this transfers the data from the 1D to 3D solver. And when you take the more important section is near to the nozzle tip section, where we have this transformation, where the exchange of data is happening near to the interface. And we can see this XD is the needle movement, 3 degrees of freedom needle movement, and the temperature of the flow field, and also the pressure. So these three data are communicated between the 1D solver and 3D solver. And the needle is in a 3 degree of freedom movement. So this is the coupling which I used here for the simulation, for the 3 degree of freedom, for the 3-dimensional movement of the needle. So for the injection test case, I considered a 6-hole nozzle with around 365,000 cells, and 2 cases, one with a symmetric nozzle case where you can see the nozzle holes are perfectly symmetric, and other case is an asymmetric case where I induced the erosion fields here. You can see in these regions. This is an induced erosion surfaces on the mesh, so that the asymmetry can develop during the flow. So these are the 2 test cases I considered for my study. One is for the 6-hole symmetric injector case, and other for the asymmetric case with an induced eroded surface on the mesh. And these are the operating conditions with a pressure of 160 megapascal, and the system is considered with liquid compressible with density varying with pressure and temperature. So the system of equations is all the mass, momentum and energy with interfacial exchanges between mass, momentum and energy, and for the enthalpy exchange it is Rance-Marshall model I used, and you can get more details in my paper, so I'm not elaborating it here. And the injection events, I consider here there are 2 injection events. One is the pilot injection event, and the second is the main injection event. And the maximum lift is for the pilot injection is around 130 micrometer, while that for the main injection is around 300 micrometer. I know this is a bit small compared to the normal conventional injectors, but we consider this for this, and also this delay is also quite small, but we consider this for the study, and the injection duration, total duration for the pilot and main injection is 2.3 millisecond, and the total computational time for both these cases is 57 hours. And this is a movie for the vapor volume fraction, and you can see this is the pilot injection, and you can see this is the asymmetric nozzle where you can see an eroded region, and the vapor is really, and the flow is really asymmetric. And now this is the main injection event. You can see the flow is really asymmetric here, and you can see now the needle is bouncing, and now it will come to the seat. To get more understanding of this movement, you can see the velocity field. This is the pilot injection. This is the main injection. And you can see at the end of the injection there is a bouncing back. You can see that we will get more idea from the quantitative analysis of the results. And this is for the pressure fields. And to the temperature. And you can see here there are really heating zones due to the flow. There is a gradient of temperature on the flow field. When it proceeds, you can see here this during the needle lift. You can see these regions due to the shearing of the shearing term from the enthalpy equation. So from the quantitative analysis, we can see if I plotted here the needle lift corresponding to the needle force, and this is the axial needle force that is acting on the needle, and this is for the pilot injection, this is for the main injection. And you can see this period, this duration, there is a bouncing from the seat. And I have plotted here for the symmetric and asymmetric mesh for the cases. And for the symmetric case, this force is negligible, but for the asymmetric case, since due to the flow is asymmetric, there is a circumferential pressure distribution which is actually shearing on the needle surface. And this sudden impact on this needle surface make a force, a jump during the needle seat. And this is more important when for the main injection event. You can see there are peak forces, but this is only for instant up to 1,400 Newton. So, so the liquid compressibility plays a major role to dampen these forces. So I have also checked in these cases with and without liquid compressibility effect. And this liquid compressive effect has dampens these forces, especially these peak forces. And this is the radial needle movement for the symmetric case. For the symmetric mesh, we have very negligible movement. This may be due to the some mesh resolution or something. So this is really negligible. You can see this is something near to nanometer, and this is really less than 1 Newton. But for the case of radial needle motion, for the asymmetric case, you can see there is a considerable radial motion near to 2 micrometer, and this is more important for the main injection event, where you can see there is a zigzag motion of the needle due to this flow asymmetry. And at some point we can see there is a force jumping near to 80 newtons. So this kind of also behavior we also observed in some experiments, which I will show you later. So in the conclusions, in this present case, we coupled a 1D, 2D, 3D simulation with a AVL fire height sim tools. And additionally, we included temperature enthalpy equation with liquid compressibility effects, where we saw the liquid compressibility effects really damps the forces. And the needle bouncing effect is really important with for the cavitation generation, which is really asymmetric for the asymmetric mesh case. And for the future work, we are working on it now. We can see this is one of the images from the Argonne National Laboratory. But even the setup is different. Here there is only one nozzle hole, but still the pattern of the injection event is similar for our main injection. Also, the velocity, it is within the range within the range of the experiments here, and also the pattern is also similar. So this is, I just shown this to give you some idea that we are all working on this field to get more insight into how it compares with the experiments. Thank you.